Hello everyone, I'm Pedro Stamoulis, and today I'm presenting the work I have done so far as part of my chemical engineering master's thesis, where I'm evaluating the possible ways of destroying PFAS through a life cycle assessment. And first, I would like to thank these advisors, Jennifer Dunn and Sabasatzi Das, for helping me out with this project so far. So first, the scenario that is considered in this project is the treatment of PFAS impacted waters through a treatment train approach, which would consist of a separation step first, and that is then followed by a destruction process. And more specifically, the recent advancements in the development of PFAS selective adsorbents that can be regenerated via a simple solvent wash now offer the possibility of obtaining neat PFAS solids by evaporating the solvent in regeneration solutions. And after that separation step has been achieved, there are three options that are considered. The first one is landfilling, which can result in leakage of PFAS to the environment. The second one is incineration, which on the one hand, it destroys PFAS, but on the other hand, it can lead to the emission of volatile fluorocarbon greenhouse gases. And the third one is the PFAS mechanochemical destruction through ball milling, which requires the presence of co-reagents. So the question that arises is, how do we evaluate the relative environmental merits of these three approaches? And the answer in this project is through a life cycle assessment, which is a methodology for assessing environmental impacts associated with all the stages of the life cycle of a commercial product, a process, or a service. And the stages of LCA are shown in this figure, and they are resources, processing, manufacturing, distribution, use, and end of life. As you know, there are a lot of PFAS chemicals, but this project focuses on two of the most abundant ones. The first one is PFOS, or perfluorooctane sulfonic acid, and the second one is PFOA, or perfluorooctanoic acid. The three disposal options are compared on the basis of life cycle greenhouse gas emissions, energy consumption, and water consumption. And for this presentation, I would like to mention that water consumption is not included due to the time constraint, but its trends would mirror those for the emissions and energy consumption. And emissions and energy consumption are expressed in terms of 1 kilogram of PFAS that is disposed. This system boundary diagram summarizes the parts of the process which are considered for this life cycle assessment, and connecting to the stage of LCA that I just described. This would be an end-of-life study on PFAS. One thing to comment on here is that ball milling is assumed to be performed on site where the separation is achieved, and then its end products, which are for the most part environmentally innocuous salts, are transported to a landfill. It is also assumed that the distance from the facility where the separation occurs to the nearest landfill or to the nearest incineration facility, that is assumed to be the same. So the environmental impact of the transportation is basically equal for the three scenarios we're discussing here, for the incineration, landfill, or ball milling on site, and then transportation to the landfill. In order to arrive at the final results that I will be presenting shortly, I developed material and energy flows for each of the three disposal options. The databases that I used to as sources for my data were GREET, Greenhouse Gases Regulated Emissions Energy Use in Technologies, and the EcoInvent models, as well as data from the published literature. sorry. Okay. And in this slide, I will talk a little bit about how I calculated the energy required for ball milling. In general, experimental work has shown that the mechanochemical degradation of PFAS through ball milling requires a core reagent. Otherwise, it's not effective at all. A lot of chemicals have been used for this purpose, but most of them are not very effective. The most effective ones I could find in the literature were potassium hydroxide, aluminum oxide, and lanthanum oxide. What complicated this calculation a little bit was that there are no scaled up ball milling processes for PFAS specifically. There are large-scale ball mills that are used for the remediation of POP contaminated solids, however. So this gave me a little bit of an idea of what this process would look like in a pilot or full-scale scenario. But for PFAS, since they're only experimental lab data, essentially, I just had to use the lab data to calculate this energy. And what I calculated was the energy dose, which is the total amount of calculated transferred to the powder. And this depends on the ball to powder ratio or charge ratio, on the ball impact velocity, which in turn depends on the revolutions per minute of the ball milling, on the ball heat frequency, and the time of milling. So this table summarizes some of the values that I got for the specific energy dose. And as you can see, we can take away two things from these tables. First, that the energy dose for PFOA is generally half of the energy for PFOS, because PFOA is not as stable, and as a result, it degrades more easily, and it requires less energy for its complete degradation. And secondly, degradation via potassium hydroxide appears to be the most energy efficient on per mass of powder basis. However, one of the last conclusion from the last slide is not necessarily represented here in my final results, where we can see that the PFAS extraction is most energy efficient with aluminum oxide. And the reason for that is that the optimal mass ratio of potassium hydroxide to PFAS is around 23. So it's much higher than the optimal mass ratio of aluminum oxide to PFAS, which is around 6. So for the same quantity of PFAS that is degraded via ball milling, we would need a much larger quantity of potassium hydroxide. This is shown by the comparison of the red bar for potassium hydroxide and the red bar for aluminum oxide, which refers to the energy consumed for the complete degradation of 1 kilogram of PFOA. The light shade of red is also lower for aluminum oxide, and this refers to the energy consumed when preparing the core reagent. So basically, according to GREET, preparing the aluminum oxide requires much less energy than getting the potassium hydroxide. And the same trend appears to be true for the greenhouse gas emissions. So those are lowest when using aluminum oxide. Now to talk a little bit about the energy consumption for landfilling and incineration. The energy consumed in landfilling is considered to be very low, so as a lower bound 0, because the fuel consumption per unit mass of waste that's transported is low. For the energy consumed in incineration, I use the carbon balance to account for this emission, and I assumed a complete incineration for that calculation. However, sometimes the incineration of PFAS is incomplete, and that can lead to PFAS being discharged into the air and contaminating nearby communities. As you can see here, the GHG emissions are much lower for incineration, even when comparing that to the best case scenario for ball milling. But as I described previously, there are some environmental drawbacks that are so to summarize, aluminum oxide probably for both concentration of potassium PFAS and seeing a similar validation. Some hydroxide with action. See that.
We appear to have lost Petros, so we'll see if he can come back in the next couple minutes. Otherwise, we'll move on. Ah, you're back.
Oh, sorry. I don't know what happened.
Yeah, no worries. Just
Can you
go ahead
hear
and
me?
get your PowerPoint started up again and start where you left off.
Okay. Where did it stop?
I think you're about at the summary.
Okay, that's good. Sorry about that. Okay. So as I was saying, for incineration, we found that the GHG emissions were the lowest per kilogram of PFAS, but there are other environmental concerns with this process. So we might need to see how we would capture those in the context of an LCA. And in addition to those methods that I've considered so far, I will probably also consider more methods of PFAS destruction to compare, and those would namely be solvent-based recovery and methanol evaporation. Okay, so yeah, this was my presentation. If you have any questions, I'd be happy to answer them.
Thank you. Reminder to our audience that you can type in your questions into the Q&A button on the Zoom toolbar. And we do have a couple of minutes for questions, so we'll let you all stew on the interesting information that Petros has provided. While they're thinking, is there anything else you wanted to share about your research?
I think that's pretty much it. I can't think of anything else right now.
Okay. Well, we can go ahead and move. Oh, there's one that just popped in. Can you go over the calculations for the low greenhouse gas emissions with incineration?
Yeah. Go back. So yeah, basically, the GHG emissions would be much lower for incineration, and the way I calculated that was basically by computing the carbon content of the average carbon content of PFAS materials, and then just doing a mole balance essentially by assuming a complete combustion. So I did the mole balance, but I should probably add to that. This is probably not where the analysis would stop in this for this calculation.